Hi everybody, I'm going to present our work titled ApproxDNN Incentivizing DNN Approximation in Cloud, which was accepted in CCGrid 2020. I am Seyed Morteza Nabavinejad from IPM, and I have co-authored this paper with Elena Mashayekhi from University of Delaware and Sharif Reda from Brown University. With the proliferation of machine learning applications, service providers have started offering them to their users as a new service. A large category of ML applications, including deep neural networks, can benefit from hardware accelerators, such as GPUs and FPGAs. Hence, service providers that rent their hardware resources from cloud tend to employ VM instances equipped by such accelerators. In this work, we focus on such service providers that offer ML as a service and want to reduce their operational costs by leveraging different types of instances offered by cloud providers, as well as the capabilities of GPU-based hardware accelerators. At the first step, we provide some information to motivate the use of reserved instances and reduce precision instructions of GPU accelerators, which are the fundamental elements of our proposed approach. In addition to conventional on-demand instances, cloud providers offer other instance types to satisfy the various requirements of users. For example, to satisfy the needs of users that want to rent instances for a long period of time, such as service providers, cloud providers offer reserved instances. These instances are offered in the form of long-term contracts, for example 1 year or 3 year contracts with significant discounts, which is sometimes up to 75% compared to on-demand instances. The service providers can employ reserved instances to cover a large portion of their computing resource demand and hence minimize the use of on-demand instances. The figure compares the price of on-demand and reserved instances of a few configurations from Amazon EC2. We can see that the difference between the price of on-demand and reserved instances is very significant in this figure. Moreover, we conducted a set of experiments to show the impact of reduced precision instructions of GPU accelerators on the accuracy and runtime of DNN inference. We employed 9 image classification DNNs with diverse characteristics. For each of these DNNs, we have its frozen graph model that is trained using conventional 64-bit floating point precision. Using TensorRT, which is a tool provided by NVIDIA, we generate their respective 8-bit integer models that can be used for inference. The inference time and accuracy of results for both precision are presented in the figures below the slide. As can be seen, the reduced precision instructions can successfully reduce the inference time with negligible impact on the accuracy of the results. Seeing the importance of reserved instances and reduced precision instructions in decreasing the cost and runtime of DNN inference applications, now we are ready to state and formulate the problem that we are going to address in this work. In our work, we consider the case where service provider employs a mixture of on-demand and reserved instances for serving the requests. The requests are the DNN inference jobs submitted by the users. By default, the DNNs are executed by default precision instructions, for example 32 or 64-bit floating point operations on reserved instances. If the resources of reserved instances is not enough, the on-demand instances will be employed to cover the extra resource need. The service provider can decide to execute some DNNs for reduced precision instructions to reduce the usage of on-demand instances, provided that the user accepts the execution by reduced precision instruction. To incentivize the use of reduced precision instructions, the service provider offers a SLA or service level agreement violation penalty fee to the users. The objective is to reduce the total cost of resources, which is the sum of the reserved and on-demand instances, provided that the jobs can meet their deadlines. In the problem formulation, the decision variables are xi, which indicates whether the job is executed by default precision or reduced precision, and the yi, which shows the type of instance the job is deployed on, which is either reserved or on-demand. If a job is deployed on an on-demand instance, it would be definitely executed by the default precision to avoid the SLA violation penalty fee, and the cost of on-demand instance can be computed accordingly. But if a job is scheduled on reserved instances, it is either executed by default precision, which again doesn't impose any SLA violation penalty fee, or it is executed by reduced precision, which imposes that penalty fee, which should be included in the cost. The objective, as mentioned earlier, is to reduce the sum of the cost of on-demand and reserved instances, provided that the submission time of the job plus its execution time is less than its deadline. Considering the problem statement and formulation, in the following we describe our ApproxDNN approach. ApproxDNN aims to reduce the employment of on-demand instances and hence reduce the total cost of resources, considering the gap between reserve price. To this end, it designed and implemented an incentivization mechanism to promote the use of reduced precision instructions. In this mechanism, a SLA violation penalty fee is offered to users, so they will accept the reduced precision. Leveraging the reduced precision allows ApproxDNN to minimize the use of on-demand instances, because reduced precision decreases the execution time of the jobs and hence the need to employ on-demand instances to meet their deadline. The amount of the penalty fee is a coefficient of the cost of executing the job with reduced precision on reserved instances. In other words, it offers the users a portion of cost saving that can be achieved by the employment of reduced precision instructions and executing job on reserved instance. Hence, the total job of executing a job on reserved instances would be the cost of resources plus the penalty fee. Note that by default, every job would be executed by default precision and not the reduced precision, unless the user agrees with it. The main challenge here is how to select the SLA coefficient or SLAP, which determines the amount of the penalty fee. The first step is to find the maximum value of SLA coefficient. The SLAP or SLA coefficient should be selected in a way that the total cost of executing the job on reserved instances with reduced precision, which is the cost of resources plus the penalty fee, is not greater than the cost of executing that job on on-demand instances with default precision. Otherwise, there is no benefit in using the reduced precision. After finding the maximum value of SLA coefficient, now it is time to find the optimal one. To this end, we first consider a model for the probability of reduced precision acceptance by users. Based on this model, the higher value of SLAP up to max SLAP increases the chance of acceptance. Based on this acceptance probability, we formulate the expected cost of a job. The expected cost is either the cost of job being executed on reserved instances with reduced precision or being executed by default precision on on-demand instances. The probability of either of these cost terms is determined by acceptance probability. Solving the expected cost by considering it to equal to 0, we can find the optimal value of the SLAP. ApproxDNN offers the penalty fee to users based on this value. and the users will either accept or reject it. In this figure, the curve of the expected cost for different values of SLAP is depicted considering constant values for other variables in the expected cost formulation. Here we can see that for a specific SLAP, the cost would be minimized, and that is the optimal value for SLAP, which is going to be selected by ApproxDNN. This illustrative example here shows how ApproxDNN leverages the reduced precision to decrease the usage of on-demand instances. If we schedule all the DNNs with default precision on the reserved instance, we see that the last DNN, the orange one, cannot meet its deadline. The conventional method employs an on-demand instance to execute the DNN, which we can see in the second row. However, ApproxDNN leverages the reduced precision to decrease the execution time of the job, and consequently, it can successfully deploy it on a reserved instance and remove the need for employing the on-demand one. In the following, the overall flow of ApproxDNN is depicted. To better see the figure, we show it in the next two slides in a larger scale. First, ApproxDNN generates the reduced precision model of the DNN and estimates the total runtime of the DNN with both precision. Based on this estimation, it first checks to see if the job can meet its deadline on reserved instance with default precision. If yes, then the job is scheduled on reserved instances and the procedure is finished. If not, then the ApproxDNN calculates the SLAP for the job considering its estimated runtime with reduced precision. Then it checks to see if the user accepts the offer for reduced precision. If the user doesn't accept the offer, then the job should be scheduled on on-demand instances with default precision. On the other hand, if the user accepts the offer, then ApproxDNN again checks to make sure that the job can meet its deadline on reserved instance, this time with reduced precision. If so, then the job is scheduled on reserved instance. Otherwise, it is scheduled on on-demand instance with default precision. It was the overall flow of ApproxDNN. Now we present the results of our experiments. We considered image classification DNNs as our DNN jobs, and for their dataset, we used ImageNet dataset. We compare ApproxDNN against three rivals: on-demand that doesn't leverage reduced precision and simply deploys the DNNs that cannot meet their deadline with reserved instances on on-demand ones; the acceptance-centric aims to increase the chance that the users would accept the offer for reduced precision, so it offers high penalty fee or high SLAP in other words. Finally, the penalty-centric tries to minimize the penalty fee paid to users, and hence it offers low penalty fee or low SLAP. For the incoming jobs, we use workload from Microsoft Azure that has the trace for VMs launched at Microsoft Azure Cloud Service. For the results, first we show the sampling results to emphasize the accuracy of the sampling method in estimating the runtime of the jobs under different precision. Then here we can see the results for the total cost for entire workload under various approaches. As you can see, ApproxDNN improves the total cost significantly compared to all the other approaches, up to 18.3%. To go into the details, we depict the cumulative distribution of different parts that form the total cost. As can be seen, ApproxDNN usually stands between acceptance-centric and penalty-centric. It shows how ApproxDNN tries to find a trade-off between resource cost and penalty cost to minimize the final total cost. Furthermore, showing the distribution of SLAP offered by different approaches, accentuates the behavior of ApproxDNN in trading of resource cost with penalty cost. The SLAP offered by it, ApproxDNN, stands between the two other approaches. Finally, we show the dynamic behavior of ApproxDNN in offering different values of SLAP and final output based on the decision of the users. As can be seen, ApproxDNN offers different values of SLAP to each job based on the gap between on-demand and reserve price, as well as the reduction of the runtime of the job when using reduced precision. If the user accepts the offer, then the job is executed by reduced precision as shown by the background column. We also did some sensitivity analysis experiments, but we didn't bring them here to avoid long presentation. They can be found in the paper. And finally, here is the conclusion. In this paper, we wanted to reduce the cost of machine learning as a service that uses the cloud resources. To this end, we employed reduced precision models of DNNs so we can execute them by reduced precision instructions of GPU accelerators. It helps to reduce the execution time of the jobs and consequently the use of expensive on-demand instances. However, using reduced precision models would affect the accuracy of results, which is not something that users would appreciate. To incentivize the users, we offered them a SLA violation penalty fee to compensate the accuracy reduction. The users are free to either accept or reject this offer. Our approach of ApproxDNN tries to find the best amount of SLA violation penalty fee such that the profit of service provider is maximized. Our experimental results using several image classification DNNs shows that our approach can improve the total cost of the resources by up to 18% compared to conventional approach that doesn't use approximation and immediately employs the on-demand resources. Thank you for your attention. Please feel free to contact me should you have any questions. Thanks a lot.